Hello and welcome to another episode. So today we'll be discussing something that is very important in our body, which unfortunately not many students know much in detail. So I made this video compiling a lot of data from a lot of places so that you actually understand what exactly it is that happens over here. So we have your sodium potassium ATPase, and we'll come to understand recent advances in it. So this is the article from which major chunk of what I'm doing is from. So in case you have more queries, you can refer to that. Okay, so basically the structure of your sodium potassium ATPase, it has a alpha unit, a beta unit. The alpha unit has a part which is transmembrane in nature, and one part which is jutting out into the cytosolic part, and the extracellular part which is there. Okay, so this is your beta, this is your alpha. You can see presence of a gamma segment over here. Okay, and on top you have some glycosylation residues over here, and there is presence of cholesterols and all that. Okay, so what you have to understand is this part, your A. Okay, so this is your beta, this is the alpha, and in the alpha we have A, your N, as well as a P domain. So these are the parts which are outside into the cytosolic domain, and above that this is the part which is transmembrane in nature. So this uh, N part is where ATP comes and binds. Okay, so that is nucleotide binding domain, N domain. Now once that happens, this A domain, which is actuator domain, that activates. Okay, so that has the phosphatase activity, and that splits ATP to ADP and inorganic phosphate, and this inorganic phosphate that comes goes to your P domain. Okay, so that is your phosphorylation site, so that is your P domain. Okay, so you have your N domain, nucleotide binding, the P domain where phosphorylation takes place, and the actuator domain. Okay, now in the P domain, this is the part where phosphorylation takes place. Above it is a transmembrane domain. Okay, so this part that you see over here, transmembrane 1 and 2, next to it the 3 and 4 part, and beyond that 5 to 10 is this region. So this 5 to 10 region is pretty important because that is the inner core where all the ions that come in are going to bind and stay there. Okay, so the binding sites for the ions like sodium potassium are over here in the center. Okay, so that is 5 to your 10. Okay, so you can see a pictorial diagram of the same thing. You can compare it over here. This is the nucleotide binding N part. You can see that the ATP is already bound over there, and we have this part which is the P part, and this is the actuator part over here, and this is the transmembrane. You can see the membrane over here, and transmembrane region consisting of 1 to 2, 3 to 4, and this is your 5 to your 10, and you can see that the binding sites are over here. Okay, so this is a very looks complicated, so I'll just simplify this whole thing and try to explain to you exactly what happens. So going on to how this actually works, you can see the ATP over here, the adenosine and the triphosphate, and once it attaches, so this state initially is what is called E1. So the first state is E1, then we have an E2 phase. Okay, two phases are there. So this is the E1 phase. So once this binds, uh, and what happens is this transmembrane domain which was there, the 1 and 2 part, that kind of moves up. So that kind of exposes parts, the binding sites for sodium. So that is especially in the M5, 6 and 8. So transmembrane domain 5 to 10. So in that 5, 6 and 8 are the binding sites for your sodium. So you can see over here, this moving up, you can see this is being pulled over here, and this moving up opens up the channel and opens up the binding sites over here. Okay, so this is because of the binding of ATP. This is the E1 phase. Because of that, in the center, sodium is going to come in. Okay, 3 binding sites are there. Now, the reason why a positively charged ion like the sodium binds, because this region is rich in aspartate and glutamate, and which are negatively charged, and because of that, that kind of makes up a whole region over there where positively charged particles like the sodium can come and stay. Okay, now once this happens, next is the actuator site over here, removing one phosphate from the ATP. Okay, so now sodium is bound over here, and this phosphate is now going to go and phosphorylate the P domain over here. And once that happens, that will result in conformational change, because this whole thing is alpha. Okay, so this P is connected to the transmembrane domains, because of which that phosphorylation will lead to a conformational change, whereby I told you earlier this was actually up. Okay, now the phosphorylation will make it come down. Okay, so you can notice here how it had changed. Okay, so that taut pulling is no longer there, this has closed, and the sodium stays in. Okay, and the ADP is still attached over here, and it is phosphorylated. So this is E1P, phosphorylated. Okay, that makes sure the sodium stays here. What happens next? Okay, so the next thing that should happen is your ADP over here is removed. So the removal of ADP from here is going to open up your outer channel, the extracellular site. So that outer channel opens up. Now the sodium goes out. Okay, now this is the time when your potassium is going to come in. Okay, now once potassium has come in, right now you might have a doubt. Okay, there were like 3 sodium. Now only 2 potassium is there. Won't there be a charge difference and all that? So this is one reason why they have postulated why there's another pathway over here through which your proton H plus can come in. Okay, so that is postulated, we're not sure yet, is postulated to play a role in maintaining the charge over there. Okay, so after potassium comes, that will dephosphorylate it. So dephosphorylating this again changes the conformation, whereby your outer channel is closed. And the next thing that happens is this should go back to your E1 stage. Okay, right now this is in the E2 phase. Okay, the outer channel opening up made it go to the E2 phase. Okay, now this should go back to your E1. What should happen for it to go back to the E1 is what I had mentioned in the beginning. The whole thing started when ATP was binding to your N part. Okay, so because of that, potassium goes out, it goes into the E1 phase, and now the whole cycle can repeat again. Okay, so isn't this wonderful? So this is one diagram from Boron's textbook of physiology. So whenever you come to learn about sodium potassium ATPase, you will see diagrams like this. Okay, so it might look very confusing. That's why I made this in the first place. Okay, so now we'll just try to look through it and see how simple we made it. Okay, so first is the E1 phase, open inside, sodium comes in. Okay, so for this to happen, your ATP must have bound to it. Okay, next what happens? This breaks, so sodium comes in, of course, and phosphorylation of this part takes place. That you can see has closed the inner gate. Now, what is not shown correctly over here is at this point, your ADP goes out over here, and that kind of opens up your outer gate. Okay, so making it E2 phase. Now sodium goes out, potassium comes in, and potassium coming in will dephosphorylate it. Okay, you can see phosphorylated part is no longer there. So that dephosphorylation closes the outer gate. Now to open the inner gate again and repeat the cycle, your ATP should come in. So potassium goes in and the cycle is now going to repeat itself. Okay, now further details. So, your sodium potassium ATP is very important in your body. Such a beautiful concept. Okay, and we cannot live without it actually. So in case you're interested in knowing a lot more about your sodium potassium ATPase, make sure to comment below and let me know Okay, in that case, I'll make another video explaining a lot of things about how sodium potassium ATPase is useful in our body. Okay, otherwise it's okay. Yeah, anyway, I hope this was helpful. Thank you.